Fundamentals here in the JPL Caltech Virtual Summer School, Big Data Analytics. I'm Chris Mattman. So in the first part of Big Data Architecture, we covered two main things. We covered sort of an introduction to software architecture, its principles, some of its research, some families of understanding of what we should be thinking about in terms of software architecture. And we sort of wrapped up thinking about things like styles, patterns, and reference architectures. Today, or in this next sort of lecture here, we're going to be covering architectural modeling and visualization. These are higher level sort of architectural operations that operate based on capturing information about components and connectors and configurations, and then figuring out how to visualize them and interact with them. And we'll talk about another thing that you see quite often, and which is another real good applicability of software architecture, which is when you have code and you have software architecture, just making sure or understanding how consistent they are between one another and identifying when they aren't and what those impacts are and what types of things you can do to sort of mitigate that. So let's talk a little bit about architectural modeling. Basically, as I stated in the sort of first part of this series on big data architecture, the Medvedevich, Taylor, and Dashfi definition of software architecture as the principal design decisions in a software system. So architectural modeling, if you think about it within that context, is really the capture, right, or the recording of those principal design decisions. You may build a UML model, and what are you doing when you capture those components or you capture the interactions between them? You're capturing the principal design decisions. You're creating an architectural model of your big data system, okay? So architectural models defined, it captures and records the principal design decisions about a software system, right? So there were several notations that have been developed to capture architectural models and instances of architectural models. Probably the most popular that you guys are all familiar with is UML. If you take an undergraduate course in software engineering, you've been exposed to UML. A lot of times, if you take graduate courses in this, you're exposed to UML. And there are derivatives of it that exist nowadays, SysML, which is the systems engineering modeling language, a number of other modeling languages that end in ML for modeling language and so forth. The UML was the unified one. It sort of was pioneered by Grady Booch and a number of other folks who were thinking about how to model software back in the day. So UML is by far kind of the most prevalent architectural modeling notation you might be familiar with. It's also by far not the best, and it has its issues and problems, and we'll potentially talk about some of those depending on how much time we have. But it's worth pointing out that UML was also emergent out of sort of a heyday of architectural modeling research back in the day, especially during the 90s and the 2000s. This is sort of the golden age of software architectural research. Right, this is the days when Roy Fielding was at UC Irvine and Jim Whitehead were there, and a number of people were, in a high-powered software engineering group. This was when there was tons of research by David Garland and sort of Mary Shaw at CMU. This is when lots of things were going on at CU Boulder with Alexander Wolf and Andre van der Hoek, and lots of sort of work going on in architectural modeling back in the day. So out of that came a series of different architectural description languages, which are really the predecessor to common architectural modeling tools. ADLs are architecture description languages. Okay? And we need ways of understanding, even though many of these aren't still in existence today, elements and principles from them have made their way into things like UML. And they've made their way into other modeling languages and notations. And it's important for you to think about ways of evaluating architectural modeling notations. So if you go out and think that you need to develop your own, or even if you're trying to pick, amongst UML versus simply doing PowerPoint or, recording an architectural model in text, all of these are viable means for capturing those principal design decisions. You need ways of evaluating why, when, how, where, why you should do it or not. And the ways that we typically evaluate them are the ability or the capability of an architectural modeling notation to capture things like the structure, the components, and the connectors, the behavior of the architecture, and to model that, like its interactions and, for example, what states components transfer between, what type of data they have, what data is shared between those states, the workflow, and things like that. So this is how we evaluate architectural modeling, and that's effectively why we need architectural modeling notations and architecture description languages. So these ADLs, which again kind of came out of the 90s and the 2000s and have since sort of emerged into architectural modeling notations, some of them back in the day in terms of software architecture research you can kind of break them down between what they were focusing on. There are things like Darwin, which was really focused on modeling components and their structures. And when you model the components and the structures, you did it in such a way that you could use a pi calculus to analyze things simplistically, like reachability of one component to another. Are these two components going to be able to communicate? It was really nice to have that in something like Darwin, because you didn't even need to build your software system per se or implement it, but from an architectural model, you could determine whether or not two components had reachability and could communicate with one another, simply by capturing one of these architectural models. Rapide took that sort of to the next level and really started to focus on interaction, having the capability to capture not just structure in terms of components and connectors, but then interaction and having an understanding of the effects of interaction, which led, when we'll talk about visualization later, to things like effect visualizations. Wright focused on components, connectors, structure, and behavior. Okay? Then we had some architecture description languages that were specific to a particular domain, like Koala, which was used very heavily to model product lines. Okay? So large numbers of product lines for televisions or for television software systems and controllers that were modeled by things like Koala. Okay? Avionics, in the avionics domain, you had things come out like the Avionics Architecture Description Language, okay, or the AADL for that. All the way to sort of the kind of common modern predecessor, and even today still now used, extensible architecture description languages. And there are three kind of main examples of that. Acme, which came out of David Garland and Mary Shaw's group. Okay, and it supported components, component types, connectors, connector types, and arbitrary properties about those components and connector types. Because what they quickly realized with early architecture description languages is you were limited to the information that you were capturing in them. If you only knew about components but you didn't know about connectors, you couldn't do downstream analyses of your architectural models that had to do with interaction. You could only do limited analyses that had to do with structure or computation. Okay? So and then in avionics, they were modeling a bunch of avionics properties in terms of AADL and other things. Well, that might not have done as great a job of modeling properties relevant to, say, data movement in those avionics systems, but it might have done a great job at modeling properties related to architectural reliability, because that was really important in the domain. So what people started to realize, looking across all the architecture description languages that were being developed in sort of this heyday of software architecture research, is that they really wanted to kind of pick the best of all of them. And so then came this sort of notion of extensible architecture description languages. Okay, and Acme was sort of a first example of that. ADML was Acme, that canonical model, represented as XML. Okay, and there was an Acme Studio that came along with that, which was sort of this Eclipse-looking studio in which you can author and create these architectural model instances that were ADML instances that had these ability to capture, for example, on a component, its memory footprint, and simply to specify that property when you have it, to maybe specify its bandwidth requirements, to specify on a connector what type of interaction protocol it has. So arbitrary properties specified per component, per connector, per canonical architectural element, and reified and really recorded in this architectural modeling instance. XADL, or XADL, is very similar to ADML, and it came out of UC Irvine. XADL did. And the screenshot here is actually a screenshot of ArcStudio 4, which is the environment in which you author architectural modeling instances that are guided by XADL or XADL. Okay? So now we're moving from architectural models and it being important to sort of capture these properties so that eventually we can do downstream analyses. And I don't cover architectural analysis here in this in the summer school because we simply don't have time, but I encourage you to take a look at some of my architectural analysis slides on my website, my USC website that I linked earlier. The whole goal of capturing these architectural modeling instances is really ultimately to have the ability to understand a lot of properties and elements of our software system long before we implement the code. Well, one thing that can really help us with sort of just interacting and looking at architectural modeling or architectural model notations driven by these architectural description languages and these architectural modeling languages, one of the things that can really help us is architecture visualization. Okay, and visualization is more than simply putting a pretty picture of an architecture up on a screen, like, for example, the one that I showed you with Tika earlier, but it's not just depicting the architectural model, but it's interacting with it. Okay, so this is what separates visualizations from architectural visualization from simple static diagrams or simple drawings. Okay, and there are sort of four kind of common approaches to architectural visualization. There's textual. Yes, some people capture architectural model instances and then visualize them in text files in a text editor. Right? We write a bunch of text. You publish a paper on an architecture in big data or whatever, and we've got text, which has a lot of information about the components, the connectors, those principal design decisions about the software system. So text is a completely valid way to visualize an architectural model. And you know what? There's a textual visualization even for things like UML, right? It's called XMI. It's called interacting, the XML metadata interchange language. It's called interacting with the UML model in largely a textual representation. Okay? There's graphical. Yes, people make PowerPoints. And there's architectural model principal design decisions in there. Okay? Hybrid, which is sort of what happens in UML. You bring together text and sort of these informal graphical notations. And then there are things called effect visualizations. And you see these when you build early on, when you build models and things like Rapid. But what they are is basically building an architectural model and then running it through a simulator. And we see these in big data systems sometimes. We take an architectural model that represents a detailed specification of the system, maybe some interactions, and then we simulate different data or operational profiles into the system to then see what types of maybe the degradation of memory over time or things like that. And so sort of effect visualizations are visualizations, what-if scenario visualizations on your architectural model that you capture for that. A lot of times when you're thinking about visualizations, there are multiple views of the same architectural model or software architecture even. These are two views of the Tika library, right? You'll notice a different number, cardinality of components and connectors from the left diagram from the one on the right. Okay, and we typically call the differences, even though there are multiple views in architectural visualization, two views of the same thing, or the fact that architectural models typically have potentially multiple visualizations, and potentially multiple visualizations represent different architectural views, a component view, a view mapping architectural components to the physical hardware, a deployment view, for example, and things like that. So again, just to sort of review, architectural model captures some or all of the principal design decisions about the software architecture, right? So you might have an architectural model that's simply focused on the behavior of your software system. You might have an architectural model that's simply focused on the structure, and so it may subset or capture just a subset of principal design decisions that have to do with that. Okay? An architectural view is a further filter, okay, a further filter of that model that you want to visualize, that is, depict and interact with. Okay? It's some subset or collection or filter, a further filter on the model. So maybe we've got the entire architectural model, and we want to show the deployment view. So it's some filter of the principal design decisions that have to do with that. Now, the deployment view is actually the deployment viewpoint, because a viewpoint is the name of that filter, the name of that sort of subset of principal design decisions that we're talking about. So the way I like to think about it is we've got an architectural model. It may or may not be a subset of all of the principal design decisions of the software system. A view is a further subset of that model, and the viewpoint is the name of that view. Okay? So we're going to move just real quickly into thinking about some higher level processes for this in terms of architectural recovery. Now that we've covered architectural modeling notations, architectural visualizations, we're going to shift gears a little bit and talk about architecture recovery. What you find is that no matter what you do, to record architectural models and do your best to think about the principal design decisions, to visualize them before you implement the code, is that when someone goes and implements the code, that code may be different than what you originally theorized or prescribed, if you will. We call this process architectural drift. Well, we call it two different things. We call it either drift or erosion. Drift is basically when the code, the as-implemented architecture, varies from the prescribed or the sort of thought of software design or based on architectural modeling notations or whatever. If that code varies from that, but that it varies in such a way that it doesn't violate any of the core assumptions of the architecture, we call that drift. And it's a subtle difference between that and erosion. Erosion is pretty much the same, that same case, except the variations in the code from the actual prescribed architectural model cause such a difference that it actually does violate like a core requirement, or it violates sort of a core fundamental principle of the software system. Either way, there are processes for dealing with architectural drift and erosion, and that process is called architecture recovery. Basically, architecture recovery is the act of recovering the architecture or an architectural model, an instance of an architectural model, from the as-implemented architecture or from the code. And this is the sort of best way to ensure that we actually know what the true architecture of the system is, because the code is the most living, canonical representation of your software system, period, right? It's what you constantly are working on. You may even have great architectural design and all these documents, but eventually you get to the code, and that's really what the investment is going to go into in terms of maintaining. So the best way is to have some process for automatically, sort of, or as automatically as possible, recovering an architectural model from that. And that's the process of architecture recovery. There are various processes for doing this that have been developed in the architecture research literature over the years, including ones by Mattman et al., Jakubik and Medvedevich et al., and various other researchers and things like that. Typically, this involves looking at the code, doing static analysis on it, determining what pieces of code talk to one another, looking at dynamic state analysis, what states are these classes or these components in, component connector analysis, which are groupings typically of kind of common classes and files in object-oriented code, or functions and procedures in procedural-oriented code, and then eventually potentially mapping it to an architectural style and things like this. So I'm going to wrap up in this module with architecture recovery, and so in the next module here, in terms of big data architecture fundamentals, I'm going to actually illustrate, in the context of big data architecture recovery, some of these core architectural elements, components, and connectors, and discuss it in the context of a real-world example. So thanks.